What is the kernel? A closer look, a deeper look at the kernel. I erased the main function that I wanted to keep, so let me rewrite it. So the final hypothesis G of x is essentially an expansion over your support vectors, alpha n star greater than 0, alpha n star, yn kernel of xn and x. So xn is the data point, the support vector, and x is the input, plus b star. And now let me remind you what the kernel is. So you have x and x prime. The kernel is surreptitiously performing the following task, but without explicitly performing the following task. You've transformed these, so you go to phi of x, and now we can allow this to be infinite dimensional because we don't actually have to do it. And you transform this to phi of x prime. This is what we call z, the feature, and this is what we call z prime. And then take the dot product, z dot z prime. And that is what the kernel of x, this is x prime, x and x prime computes. So you can think of this as a black box, which sort of represents what the kernel is effectively doing, but it doesn't actually do that. It bypasses the transform and directly gives us that number. But at the end of the day, it's giving us the dot product in some space. So in this space, it can be infinite dimensional, but for visualization, let me just draw it as if it's finite dimensional. So in that space, you have z, and you have z prime, and the dot product, z dot z prime, is just equal to the norm of z prime, the cosine, let's call this angle theta z z prime, the cosine of theta z z prime. So up to norms. So if we were to normalize z and z prime, so if we did z over norm of z dotted into z prime over norm of z prime, then this is the cosine of theta z z prime. And let's look at what this cosine does. So when z and z prime are on top of each other, z and z prime are on top of each other. When you normalize them, they're the same unit vector. This is 1. So this is 1. So cosine of theta z z prime is equal to 1 when z and z prime are basically identical. Up to the normalizing. And when z and z prime are in the opposite direction, maximally dissimilar, then the cosine is minus 1. Z is not approximately equal to z prime. Modulo the norms. Of course, there's a norm here, but basically, you can think of the cosine of this angle as a measure of similarity. It's sometimes called the cosine similarity. So this is up to the norms, z prime, a similarity, what's called the cosine similarity between z and z prime. So the kernel, which is computing this, providing that you can compute a size of z and z prime as well, which is, what is the size of z and z prime? It's just the kernel of zz, square root, and the kernel of zz prime, square root. So this is, the square root of the kernel of zz, and this is the square root of the kernel of, xx, and x prime, x prime. So modulo the norms of z, the kernel is essentially computing a measure of similarity. The kernel is essentially computing a measure of similarity. The kernel is computing a measure of similarity. Let that sink in a little. The kernel is computing a measure of similarity. And so then what is the final hypothesis? The final hypothesis, you can think of as it identifies a set of important data, the support vectors. So the final hypothesis finds important data, i.e. the support vectors. Now, when you give me an input, I compute the similarity to that data point, that important data point. Okay, I weight it, okay, and then I have my, bias, but I'm basically computing a weighted similarity to a bunch of data points. So, finds the important data points, okay, the support vectors, and then computes a weighted similarity to those data points. Okay. And so any inner product algorithm, and the linear model is very similar, okay, so any inner product algorithm can be converted, can be kernelized into this form, and is essentially a similarity-based method. So, in order to design a good kernel, okay, all you have to do is design a good measure of similarity, okay, and ensure that the properties of symmetry and positive definiteness hold, in which case that measure of similarity corresponds to some inner product in some space, usually infinite dimensional, and then you can roll out all the power of the optimal hyperplane, and it, at the end of the day, is just an optimal version of a similarity-based method. Okay. That finds the hyperplane in that weird space for which this similarity kernel corresponds, okay, to which this similarity kernel, if you were to transform, would compute the dot product. Okay, so we roll out the support vector machine, the kernel machinery, and we're essentially running a similarity-based method where we identify the important data points, similarity to those data points, weighted similarity, boom, that gives you your classification. So we started with similarity-based methods and said, oh, that's the simplest thing you can do. And we've gone full circle because RBF network we did, neural network we did, and then now the support vector machine can simulate both of those, and you can put any kernel you want, which is a similarity. Okay, and so everything can be done with this similarity-based approach, okay, optimally. And at the end of the day, we have a similarity-based method. We've gone around full circle. We started with similarity, did complex things, and we're back at similarity. And we might think to ourselves, well, we shouldn't be surprised because what else is there? I give you data and I ask you to predict on a test point. Okay. Essentially, the only thing you can do is, which leverages the data, is to say, well, my test point is similar to what data points, and then I'm going to use those to classify. What else can you do? And if there's no such similarity measure that you can sort of implement, that says that, if your test point is similar to your data points, then the test classification should somehow be related. If there's no such relationship, then there's essentially, in some sense, no target function. The problem is unlearnable. Okay. So for learnable problems, essentially, everything is a similarity-based method. It's just that we now have a machinery that makes it all clean, optimal, algorithmically efficient. Okay. And in order to now run this machinery in any application, all you have to do is define the kernel, i.e. figure out what's a good measure of similarity for your problem. So, using kernel machines. Using kernel machines. One, for your problem, what is a good measure of similarity? Okay, so figure that out. And two, for that measure of similarity, okay, is it plausible that a linear model will work in the corresponding feature transformed space? Will a linear model work in the feature transformed space? You almost don't have much control over this. There's almost nothing to do here. You just have your measure of similarity, and if it's going into an infinite dimensional space, then you can certainly always separate. But if you use the soft margin, then you run it, and does it give you good results? Okay, will it fit well? Okay. And so the real challenge or the real task that you face if you want to run the whole support vector machinery, the whole kernel machinery, okay, is to come up with the right measure of similarity, i.e. the right kernel. And so now let's see a few examples of this, and then that'll end today's lecture.